How's the semester going? It's okay? Yeah. Okay. Yeah, well, what other classes have you been taking? What? Okay. Okay. All right, cool. Okay, so let's get started. So last lecture we discussed how to discuss the Wells linear response equation. Basically, how does the statistics of a quantity of interest change when we perturb some parameter of the governing equation. And we also discussed how to make numerical evaluation of the Wells formula easier or faster, right? By performing an integration by parts. But that depended the equation we used the last week depended on the fact that the equilibrium measure is uniform, right? So we can actually do the integration by parts easily. So today, this is probably one of the most difficult lecture to understand. But like after this lecture, I think things are gonna go easier. But today we're going to discuss the case of non-uniform density. How do we make Wells equation easier to integrate when we cannot assume that the density is uniform? So let's first take a look at what happens. What exactly is the density going to look like when the equilibrium measure is non-uniform, right? Okay, so for example, this is an example of when we take the again the sawtooth map, and we did change the objective function. So we did change the dynamics. So S is the parameter that, let me see, where is S? Yeah, so we changed the parameter S, that's the perturbation, that's sinusoidal perturbation, from 0, right, the original sawtooth map, to 0.1. So we have been slightly perturbing the sawtooth map, and we obtain, after 4 iterations, we obtain the equilibrium density that is higher in the middle of the domain and lower at the 2 ends of the domain. Okay? But what I'm going to be discussing today is that it's an even more general case. It's a case that instead of looking at just the sawtooth map, we'll focus on a 2-dimensional version of the sawtooth map, in which one of the dimension is exactly the same as the sawtooth map, but they are the other dimension, right? Instead of an expanding dimension, it's a contracting dimension. So we'll actually slowly going into the most general case of a chaotic system that has a expanding dimension, that has a contracting dimension, and in the future, when we are looking at a continuous time dynamics, it also would have a neutrally stable dimension, the time evolution dimension. So let's take the same dynamics actually and code up the version, the corresponding version, right, that has a contracting dimension. So let's imagine, let's imagine we start from a random, 1,000 random initial conditions, and we are having 2 dimensions. The first dimension being the unstable dimension, the second dimension being the stable dimension. Okay, so we take 10,000 iterations, and the unstable dimension is going to be the same as before, 2 times x plus 0.1 times sine of 4 times the unstable dimension, right? So that's the perturbation we are putting. And the stable dimension is equal to the stable dimension divided by 2. So we're contracting by a factor of 2, right, in the stable dimension. And then it is added by, so this is percentage pi. Instead of percentage pi, I divide by pi, get the integer portion of the other dimension. All right, so this is basically, it's going to get us a distribution, right, in the two-dimensional space. And we are going to record the distribution using a histogram. So using a two-dimensional histogram. So let's say we initialize the histogram with a bunch of zeros. Let's actually make a 200 by 200 array storing the histogram. After every iteration, we say histogram is plus equal to histogram 2D, and we have a okay. So the histogram would have the first dimension. I want the first dimension to be the stable dimension, the second dimension, the horizontal dimension, being the unstable dimension. So the vertical dimension is the stable one, so x1. The horizontal dimension would be the unstable dimension, and so the bins would be, for the stable dimension, would be I think it goes from 0 to 2, right? Because the for every time the second part is either 0 or 1, right? The first part also would go from 0. The first part would also go from 0 to 1. So the maximum, the vertical dimension is bounded between 0 and 2, and the horizontal dimension is bounded between 0 and pi. All right, so that's going to be the histogram. We'll take the the first entry is the actual histogram. The second return value is the bins. Okay, and I'll divide this by the number of iterations. Actually, that's right. Okay, so let's run it, and that's fine. All right, so let's run this, and afterwards we are going to visualize the histogram to see what it looks like. Color bar. Okay. Yeah, so this is what happens with the two-dimensional histogram. Okay, and actually I shouldn't really divide this by 10,000, because this is the number of iterations. We also need to multiply by the number of bins, which is actually a lot. So let's just say I am show histogram times the total number of bins, which is 200 by 200. So this is going to be a visualization of the density, right? Just to make sure I'm doing this correctly. So first of all, let's actually make sure that the case when we have a sorry, let's stop this. When we have a 0 perturbation, we should get a uniform density, right? We should get a density that's basically 1 divided by the spatial domain. Let's see, which is why am I not getting? Okay, so the histogram is the distribution. Okay, so yeah, so I need to also divide by 1,000, which is the number of initial seeds, right? So that's going to get us dividing by these, and then I need to divide by the size of the bins, which is going to be divide by pi over 200, and then divide by 2 over 200. So that's going to be the actual. Did I run this? No, I didn't run this. So I run this, then I run this. I should actually get a very uniform distribution across the domain. Yeah, so the value I get is about 0.16, which is consistent with the spatial domain that goes from 0 to 2 on the y-axis and 0 to pi on the x-axis. So this number is about 1 over 2 pi, right? Okay, so that's for the unperturbed case. So now let's look at our perturbed case. And the perturbed case is actually a very general representation of what happens when you have a chaotic dynamics with expanding and contracting dimensions. So remember, the x-axis represents the expanding dimension, the y-axis represents the x-axis is expanding, y-axis is contracting, right? So what you see is the two dimensions behaves very differently. Particularly the y dimension, which is the contracting dimension, shows very little continuity, right? Instead, it shows almost a fractal behavior in the contracting dimension. While in the expanding dimension, if you just take one slice of the expanding dimension, we actually get a smooth distribution, a differentiable density. So it's not obvious here because of the noise, but if you use longer and longer simulations, you're going to see the density along the x-axis, the expanding dimension is going to get smoother and smoother. Okay, so let's think about, in this case, right, how do we evaluate Rell's linear response formula? Okay, so that is when we have a density that is first of all non-uniform, but also even not continuous in one of the dimensions. How do we deal with that? So again, let's first write down Rell's formula. So the derivative of our time averaged object function with respect to parameter perturbation in S is equal to the summation of I goes from 1 to actually 0 to infinity, what we call dj bar, the ith term in the Rell's formula. And what is that ith term? The ith term in the Rell's formula is an integration over the whole phase space of the derivative of a future objective function, right? This is the derivative. All right, okay, the derivative times the perturbation times the okay, so this thing evaluated at y, and times the derivative of the perturbation, a derivative of this map evaluated at x, and then integrated over the whole space. So remember, this integration over the whole space can be evaluated at x or y. It doesn't matter, right? Because of the equilibrium nature of the density. So in the previous case, when we are looking at just the one-dimensional map, we use the d rho x because of the map being not invertible. But when we focus on a two-dimensional map like the Baker's map we are looking at here, it's more convenient to write this integral in terms of a d rho y, where x, so here x would be equal to the inverse map of y, right? So in the non invertible case, we can only write the independent variable as x because but in this case, we can write the independent variable as y because now x can be written as a function of y, right? So that makes the potential integration by parts a lot easier. All right. Okay. So what's interesting here is that in the previous case, when we have a uniform density, we basically just did the integration by parts on the whole domain and moved this derivative into this function, right? Because the d rho y is just a dy when we have a uniform density. But in case where the density is like this, integration by parts doesn't work, right? And in particular, we cannot even write this d rho y. So we cannot write d rho y as a density at y times dy. That doesn't even work because the density may not actually exist. If you remember previously when we are looking at the Baker's map, we did look at the contracting dimension, right? In the contracting dimension, we saw that we can get a fractal set as the possible locations for the contracting dimension. So if we have a fractal set, if the dimension of the attractor is not two-dimensional, okay, then the density would actually be infinity, right? So think about an example where we have a one-dimensional structure in a two-dimensional domain, and all the points, all the equilibrium density is completely focused or completely reside on this one-dimensional manifold or one-dimensional line. Then you can ask, what is the density of that distribution over the two-dimensional domain? And the answer would be, well, it is either 0 or infinity, right? Outside of that line, it is 0. Inside the line, it is infinity, because you cannot you cannot use a finite density to represent the density over a lower dimensional object, right? So it's essentially something similar to a Dirac function which is either 0 or infinity. In the one dimension, it is a representation of a distribution over a zero-dimensional object, a point, right? And if you look at the density over one-dimensional line, you get this 0 or infinity Dirac delta function. So this is similar here. If we have an attractor like this, where the density actually lies on the lower dimensional object, because I mean a lot of the space has gaps of 0, right? 0 density. So this is a case where we cannot even represent the density in terms of a finite valued function. So we cannot just naively write the d rho y in terms of the density and then do integration by parts. Instead, we have to really decompose this integral into an integral over x and over y independently. Okay, so we have to decompose this two-dimensional into two integrals, one integral over x and one integral over, so one integral over, I shouldn't say x or y because I'm using x and y here, one integral over the vertical dimension and the other integral over the horizontal dimension. And then we can perform integration by parts. Over which dimension can we do integration by parts? Should we do integration? I mean, so when we do integration by parts, right, we have to move the derivative onto the other part which contains this rho, right? So that requires the rho to be smooth, right? So if we do integration by parts, should we do integration by parts in the x direction, which we would get an x derivative, or should we do it in the y direction, where we get a y derivative? If you want to take derivative of this function, would you do it in the x derivative or y derivative? You do want to perform a x derivative, right? Okay, so essentially that is what we want to decompose this integral in the linear response equation, right? We want to decompose the integral into two directions and perform integration by parts only towards the x direction. So in general, the decomposition of an integral into multiple directions is called the disintegration. Okay, disintegration is almost trivial if we have just the two coordinates, where we can write, for example, our previous case, we have dji. We can write, first of all, integration into in the context of this code, right? We have the x1 direction being let me just write it as y1 being stable, right? Where we don't want to perform integration by parts. And then we have an inner integral that's over y2, where we do want to perform integration by parts. And then we have this, the derivative of j compound with phi for I times, evaluated at y, right? Now the y is basically has two coordinates, y1 and y2. The derivative, or the gradient of that, right, multiplied by the perturbation of the map evaluated at x, which is the pre-image of y. So or I can just write as phi inverse of y times d. Now the integral has been split into two parts, right? So first of all, I have the d rho of y2 inside, and then I have the d rho of y1. Okay, and it turns out that this d rho of y2 actually depends on y1, right? Because this is this d rho of y2 is known as the conditional density. It is the conditional density of y2 while fixing a y1. And if you think about this conditional density intuitively, it is taking one slice of the x of this, basically fix a vertical dimension and slice it on this plot and look at how the density varies across the horizontal axis. And this conditional density in the inner integral is the smooth density where we can perform integration by parts on. Okay, any questions on this part? Okay, now let's figure out how do we use this integration. And let's first consider the case where our perturbation, right, is purely on the unstable direction. So here, the most general case, the perturbation, right, this actually phi is a two-dimensional, it's a map from a two-dimensional coordinate into a two-dimensional coordinate, right? So this perturbation actually contains two components, one component in the vertical direction, one component in the horizontal direction, which is smooth, which is unstable and smooth. So in the most general case, we want to decompose this perturbation also into two directions, one along the unstable direction and one along the stable direction. The perturbation on the stable direction we are going to see later is actually pretty trivial to deal with. We can deal with the stable perturbation using the traditional way of doing sensitivity analysis. So let's forget about that part for now and only look at a perturbation along the unstable direction. So what I'm saying is that this derivative, the perturbation is equal to two components. The first component is going to be zero. So with respect to the outer integral, is going to be zero. So there is only a component on the unstable direction. Okay, let's see. So which is the first perturbation being zero. So that means this vector product between the gradient and the perturbation can be written as a scalar product only on the second dimension, right? So essentially what I'm doing here is I'm by this simple assumption that the perturbation is only on the unstable direction, I'm changing the vector calculus into scalar calculus so that we can just purely focus on the inner integral. Okay, so that is going to get us integration in the y1, which is the stable direction, times a y2. So this is the this is dy2, only the second dimension of J compound with the map for ith time, right? And times this component, the only non-zero component, and times d rho y1 as a function of y2. And this now integrated over the non-smooth component. And for the smooth component, we can basically rewrite this as a density, right? So basically the conditional distribution does have a density. And we have dy2 over here. So this basically, the goal of all of this rewriting is basically convert the inner integral into an integral over this unstable coordinate, right? Where there is also a derivative on the unstable coordinate, and the integration is over also, it's almost like a uniform density case, except for there is a density function going inside of the integrand. So this inner integral is now ready for integration by parts, right? Remember, what is the motivation for integration by parts? Is that this function, the future quantity of interest, is a very oscillatory function, right? So when we take a derivative on the oscillatory function, we get a very high derivative. So we want to move the derivative onto the other part, which the other part is independent of I, right? So we would not get a larger and larger integrand as I look at more terms in the Royle's linear response formula. Okay, so how does the integration by parts work? It works by just keeping the outer integral to be the same, and the inner integral, again, we look at only the non-boundary terms first. The integration over y2, we have a minus sign coming out of the integration by parts. The future objective function now gets out of the derivative, and the remaining part goes into the derivative. Right, so this is basically the inner integral is something very similar to what we got on the last lecture. The only difference is that there is this additional density, that's the conditional density over the unstable direction, conditional on a particular coordinate of the stable direction. Okay, so this is the only additional term we get compared to what we had on the last lecture. So let's focus on figuring out what that derivative that contains this additional term would give us. Okay. So this derivative, because it is a derivative of the product of two things. One is the perturbation itself, and the other term is the conditional density, right? So using chain rule, the derivative of the product can be written as a sum of the contribution from the first and the second term in the product. So this purple term is equal to the derivative along the unstable direction of the perturbation. Just the right. So it's the derivative of the unstable perturbation along the unstable direction times the density, plus the second term is that the perturbation itself, but not the derivative, and then times the derivative of the density itself. Okay, so we already have encountered the first term in the last lecture, but the second term is new, right, for us. Okay, and let me stop a while and interpret these two terms for you a little bit to give us a little bit more intuition on what they are. So if we, for example, focus on the map, just the unstable dimension. The unstable dimension, right, has these two branches that, so let's say this is x2 and this is y2. Okay, so that's basically the dynamics along the unstable dimension. The first term is the derivative of the perturbation. So if the perturbation, for example, is like that, as we discussed in the last lecture, if the perturbation is like that, then the first term represents whether the derivative of the perturbation is positive or negative. Or in another sense, does the perturbation make the derivative of the map higher or lower? If the perturbation makes the derivative higher, then this term would be positive. If the perturbation makes the derivative, makes the slope of the map lower, then this term would be negative, right? And intuitively, the change in the derivative changes the density on the y-axis. So, for example, if you compare the green curve versus the purple curve, at this location, the purple curve decreases the derivative, making the slope shallower. As a result of that, the same region in y is going to be mapped from a narrower region in x, right? And assuming the distribution on x is the same, decreasing the slope would increase the density in y. Right, so the first term in these two-term series represent the change in the density at the y location due to a change in the slope of the map itself. This is very similar to our, remember, like when we were discussing time dilation for the for a periodic limit cycle, right? Any perturbation that makes the time evolution go slower would locally increase the density and there boost the local contribution to the objective function. So that's the same thing here. Now, what is the second term? The second term is related to the magnitude of the perturbation times the derivative of the density. Okay. So this is saying that if the perturbation is positive, okay, if the perturbation is positive, then instead of mapping from the green x location, I'm mapping the density from the purple x location, right? So the second term represents a shift in where the density comes from. A positive value of the perturbation means a negative shift in the location from which the density got mapped. So if there is a positive gradient, right, in the density, okay, that means the same location y would be mapped from a lower density region, right? So if the density would go like that, so if this is the density rho as a function of x, of course, if we have a invertible map, then the same location in y would also have an increase in density, right? So basically, the density derivative would be positive, and multiplied with the positive shift, we would get a positive contribution, which taking into consideration of the negative sign means we get a lower density on the same y location. So these two terms, one represent the resulting, the effect of a changing slope. The other term represent a changing value, which leads to a shift in the location of the map. Okay, so now we know these two terms in the formula after integration by parts, and we actually already know how to evaluate the first term. And now let's shift on figuring out how to evaluate the second term. Okay, the first term is actually easier to evaluate because we are integrating over the density. And usually, how do we compute an integral over the equilibrium density? Right. So since we have done a lot of calculations for chaotic and ergodic maps so far, right? So what are the options for computing an integral of some quantity over this equilibrium density or equilibrium measure? Sampling, right? And what is the easiest way to sample while making sure that the density of our samples actually follow the equilibrium density? We just follow a trajectory, right? We just follow the dynamics and evaluate a long trajectory, and whether we start from a random collection, a random ensemble map for many times, or we even start with just the one initial condition and sample along the long trajectory, or we start from an ensemble and sample along an ensemble of trajectories, we actually get the same thing. We always, by the ergodic property of the dynamics, doing any of the three things, right? Ensemble or time average, or ensemble and time average, we are getting we are able to basically integrate over the equilibrium measure. So the first term can be easily computed. We just compute this and compute this, multiply them together as we did on Monday, right? And just average over a long or many long trajectories. But the second part is not as easy to evaluate, because if you substitute the second part into this equation, we still have an integral over d rho y1, right? So this is y1, which is the stable coordinate. But we don't have this d rho y2. So the product of rho y2 and rho y1 is the equilibrium measure, right? But since in the second term we no longer have the rho y2, so we only have rho y1. So the second term is not a function evaluated over the equilibrium measure. So we have to figure out a way. So if we still want to compute the integral in the most convenient way, which is sampling over one or many long trajectories, we have to convert the second term into a form that has a d rho y2, right, in this equation. So we do this by actually almost a trivial way. So this is equal to, we just write down what this is. So this is actually phi2. is actually only the unstable perturbation, right? Okay, and we are going to write down the ratio of the derivative divided by the conditional density itself, and then multiply by the conditional density. So because we are dividing and multiplying by the same thing, this is of course equal. And then if we are able to evaluate this part, right, then the second term after the integral is just an integral, or it's just an integral of this function over the equilibrium measure. All right, does it make sense? So now the focus is how do we compute this part inside the bracket. What's inside the bracket has two things. One is the perturbation itself, which we know is easy to compute if we know what is the perturbation, right? And of course, in this case, the perturbation, right? We always know like what is our parameter s and what is the derivative of the map with respect to the parameter. So this term is even easier to evaluate than what we did in the last lecture. But what is new is the second part. So let's think about what is the second part. It is the ratio of a spatial derivative of the density over the density itself. Right, so let's actually write it down. So that's what we call the fractional density gradient. Okay, so it is the derivative in the unstable direction of rho conditioned on y1, y2 over rho conditioned on y1, y2. So it is the derivative of something divided by that something itself. What does that mean? This kind of ratio, the ratio of a derivative of a function over the function itself, is usually called a fractional derivative. And why is that the case? So in the numerator, it represents the change of that function. Right? In the denominator is that function itself. So if the function changes by, it is really the percentage change or the change of the ratio of change to that itself. In some sense, no matter what the dimension of that rho is, right? The fractional derivative actually always has a dimension of 1 over the coordinate, the spatial coordinate. Okay, so it is basically how fast that density is changing in percentage, in relative terms, as the unstable direction increases. So the question is, now we understand what this quantity is. We need to figure out how to compute this. And in order to figure out how to compute this, let's first figure out how the density itself evolves as the dynamical system evolves. So for an actually this is the conditional, how the conditional density evolves, right? Okay, so we know that if we have a x1, x2 is mapped to let's say phi of x1, x2 is equal to y1 and y2. Let's figure out how does the conditional density of y2 depend on the conditional density of x2. Okay, and in this particular case, we know that we know phi2, just the second dimension of x2, is actually just equal to y2. And now let's start from here and figure out how the density actually relates to each other. The density always follows what we know. The density of a map follows what's known as the Frobenius-Perron equation. So that equation is saying that the density of y and condition on y1 is equal to is equal to a function that depends only on x1 and y1. So let me say a of x1 times the density condition x1 of x2 divided by the slope of the map. Okay, so what that means is that, let me say, if this is x2, the unstable dimension of the previous iteration, and this is y2, the unstable dimension in the next iteration. Okay, if these two have a function like this, right? And this function actually depends on what x1 is. So for different x1, this function might be different. Then the density in y2 is going to be equal to whatever the density in x2 is divided by the slope of this map. Right? Okay, so, and the only reason there is a multiplying in x1 is that in the x direction, you might be defining the measure, the outer measure, right? D rho x1 versus d rho y1 in a different way. So we don't really care about this multiply because it doesn't depend on x2 or y2 here. So the density here is how many of this ensemble, what is the fraction of the ensemble lies within a fixed fraction in y2, is equal to what is the fraction of the ensemble that lies within the fixed within the unit of x2 divided by the slope. So the slope really is a ratio of how big a dy2 is compared to how big a dx2 is, right? Because 1 over phi2 prime x2 is equal to basically dx2 over dy2, right? And the density at x2 is essentially the mass divided by dx2, right? And the density of rho at y2 is equal to the same mass divided by dy2. Okay, so now with this formula, the next step in deriving the fractional derivative in the density is basically just to take derivative of this formula with respect to y2. Okay, so let's do that. The derivative of the left-hand side with respect to y2 is going to be equal to, because the a just carries over, it doesn't depend on y2, so we just carry this. But x2 does depend on y2, right? So, and we know that to translate the dy2 to dx2, we need to multiply dx2 over dy2 and the derivative of the ratio with respect to dx2. right? Do you see what we have here, right? So basically, we took the derivative of the left-hand side with respect to y2, and through this ratio, we change the dy2 to dx2, and we take the derivative of this, right? Okay, and that gets us the a, and this ratio is 1 over phi prime, and then the ratio has two terms. One term is the 1 over another phi prime times the fractional derivative of x. Okay, and the other term is the density itself times the derivative of 1 over phi prime. Okay, and the final step in deriving the fractional derivative is to divide the derivative by the density itself. And here we can see the cancellation of this a. So we divide this by the density itself, and what we see is that, and we actually need to use this formula here. So the a would cancel out, right? And the one of the phi primes would cancel out. And what we get is the first part is just going to become rho on x, and then the second part just carries over, right? The second part carries over, which means let's just copy this. Okay, so this and this is actually the density gradient, the fractional density gradient at x, right? So basically, we have an iterative formula. The fractional density derivative at y is equal to the summation of two parts. The first part is the fractional density gradient at x divided by the slope of the map itself, which is for expanding dynamics is greater than 1, right? So this first term keeps decaying. And the second term is this and this actually cancels. The second part is just the d dx2 of 1 over phi prime of x2. Okay, so this derivation gives us a recursive formula for computing this fractional derivative. Okay, so basically starting, if we have the fractional derivative at the previous step, okay, the next step is equal to the previous step divided by the slope and added with another quantity. Sorry, this is actually here. This wouldn't appear here. So yeah, so because in the second, this actually would cancel with this part, which is the rho x. Okay. Now, what's interesting is, for example, when we proved that for the unperturbed sawtooth map, remember we had the formula, we had a proof that the equilibrium density is uniform. And how do we prove that? We prove that by assuming we have an initial density with a finite derivative. And for every iteration, we show that the derivative decreases by at least by a factor of 2, right? And that proof is actually embedded in this formula, because for our unperturbed sawtooth map, this derivative is equal to 0, right? Because the slope of the map is uniform everywhere. So the derivative of 1 over the slope is 0. And we see that for every iteration, the fractional density gradient at the next step is equal to the fractional density derivative at the previous step divided by 2. So every iteration, the slope decreases by 2. All right. And now when we have a non-uniform slope, there is this second component coming in. So we are no longer going to get a 0 fractional density derivative. But this recursive formula, actually by the same logic, is exponentially insensitive to how much error you have in the initial fractional sensitivity derivative, which means like you can actually initialize your fractional density derivative with any value like 0 and use this equation to iterate, and you're going to exponentially faster converge to the correct fractional density gradient. Right? Make sense? Okay. I mean, the rigorous way to prove that is that assuming your numerically computed fractional density derivative is a certain quantity, let's say called A, and the exact fractional sensitivity derivative is another value, let's call B, right? The difference between them is the error, and the error would follow an equation. That's the difference between this equation and another equation, which is the same except for this fractional density derivative is either A or B, right? Your numerical or exact. If you subtract these two quantities, the constant term that doesn't depend on if your density gradient is exact or numerical disappears. So you would have just the first part that dictates that the error would decrease exponentially. Okay, so let's actually, so this is a long derivation. Sorry for that. If you have any questions, I think it'll be really useful to kind of go over the derivation yourself again. But let's actually see how this formula actually works numerically. Okay, going to our example, right? So we have axis, but we should also have what I call G. G is the fractional density gradient. And again, we pay. So we know we can start with anything. So we make a 0. Zeros. Okay. So that's the numerical fractional density derivative in the unstable direction. Okay. So I want to make a histogram of X. I also want to make a histogram of G. So what is the histogram of G? The histogram of G is going to be this fractional density gradient multiplied with the equilibrium density. Okay, at each location. So we will see how to compute that. So the histogram of G, as you end up seeing, is going to be just the derivative itself without the fractional part. Okay. So when we make a histogram, we make it histogram of X. Now, before we evaluate X, we also want to evaluate G. So let's follow this formula. Okay. So for this formula, we want two things. One is the 1 over the slope of the map. And another thing is 1 over the slope of the map, the derivative of 1 over the slope of the map. So let's compute the 1 over the slope over slope. Okay, the slope, if you look at this equation, is equal to 2 plus 0.1 times cosine of 4 times x0, right? So that's the slope, and times 4. That's the slope, right? It's just the derivative of the unstable dynamics. In order to take another derivative, so that's the slope, and we have the 1 over the slope. Okay, in order to take the derivative of the 1 over slope, we actually just add another thing, add this e to the minus 100j, add the imaginary component onto x. and as a result, the imaginary part of this 1 over slope is another derivative of the 1 over slope, right, with respect to this parameter x times e to the minus 100. So when we evaluate our g is equal to our previous g multiplied by 1 over slope dot real. So that's the 1 over slope itself. And then plus the derivative 1 over slope dot imaginary divided by 1 e to the minus 100. All right, so that's just the formula for computing g, right? That's, I mean, like we had a long derivation, but the application of the derived formula is actually pretty easy, right? Okay, and then we have a histogram of x and we have a histogram of g. So it's going to be the same, except for I'm going to be still taking a histogram of x, but I'm going to be weighted by g. Okay, so that is whenever we are accumulating, whenever we have an x that appears in one of these 200 by 200 boxes, I'm, instead of adding a value of 1, I'm adding a value of g. Okay, so what we end up getting is going to be the g at that location multiplied by how often x appears onto that location, right? So if x appears twice, then that g is going to be accumulated at that location twice. If x appears 1,000,000 times at that location, that g is going to be multiplied by 1,000,000, right? It has accumulated for 1,000,000 times. So the end result is the local g multiplied by the density. And if you look at what g is, that's going to be multiplied by the density. It's going to be the density derivative. Okay, make sense? Okay, let's run this. Unexpected. Oh, maybe it's called weights. Okay, and then let's actually make 2 figures. And we're going to show a hist of g. Oh. Okay, so it's just let's just make 2 figures 1 by 1. Okay, so this is the original density, and this is g. All right, and let's just maybe spend a little bit time looking at what this actually is. So if you look at a particular location, for example, along this line, right, when the at between 50 and 75 being in the vertical direction, you see the density is pretty low on the left, and it increases and then decreases, right? That means the density gradient should be positive over here and negative over here. And if you zoom over here, it's exactly what's happening, right? We have a positive density gradient over here and negative density gradient over here. And to show things a little bit more quantitatively, let's actually sum up. Let's look at the marginal density over just the unstable direction. So to do that, we just plot the x-axis goes from 0 to pi, and the histogram of x dot summed over the stable direction. So that should be what we have actually shown before, right? Again, I think we need to divide divide by pi over 200. Okay, so that's roughly the marginal distribution that's summed over the unstable direction. So if you use more and more points, you should see this gets smoother and smoother. And now let's also plot the G summed over the unstable direction. So that's our right. So the derivative of the density summed over is equal to the summed derivative of the density, right? The summation and the integral and derivative on the other dimension exchanges, right? They commute. So what you see is basically when the derivative of the density gets the largest, the G also gets largest. And this also shows you how the superiority of deriving the density gradient using this way compared to evaluating the density gradient with a finite difference, right? So if you actually plot, let's actually do a central difference, for example, of the density gradient using, let's say, marginal density is equal to this, and marginal density 1, actually 2 if I want to do central difference, and divided by 2 times the spatial extent, which is 2 times pi divided by 200, right? Let's actually give it dot. We should see that about the finite difference evaluation is kind of agrees, but the noise is actually a lot larger than the G we evaluated using the same amount of data. Okay, so that's basically like how we evaluate the fractional density gradient, which is a critical component of how to evaluate the linear response formula. So to recap, we took the Rao's linear response formula, we did a disintegration so that we can perform integration by parts in the inner integral, which is along the unstable direction. Okay, and after integration by parts, we got 2 terms. One term is consistent with what we had on Monday when the density is uniform. The other term involves the fractional density gradient. And we also then figured out a way to compute the fractional density gradient. So next, we are ready to make Rao's equation easier by plugging in the plugging the fractional density gradient. So let's actually illustrate that just on the computer. Okay. And basically, let's actually copy the same code over here. And here, we are going to set S is equal to 0.1 and further evaluate the density, the sensitivity with respect to the same S. Let's see. So we are replacing the 0.1 with S. And here, we no longer need the histogram of X or the histogram of G, right? What we need is the objective function. So let's say the objective function in this case is equal to J is going to be, let's say the objective function is an array, and J dot append. So again, we are going to be using the same cosine of 2 times x0 as our objective function for now. Dot mean, so I'm averaging this, right? And yeah, I want to look at what is the sensitivity of that objective function to a small change in the parameter pi. Okay, and so going back to Rao's formula, and after the integration by parts, we have basically we have multiple terms. Each term is the product of a future objective function and one of these two. So the first task is to evaluate this future objective function, right? Okay, so basically we'll show that there is a simplification further, but right now let's just do it in the following way. J goes from 0 to, let's just take 5 terms for now, okay? And the J future would be equal to let me say x future, right? Let's set x future would be equal to x0, and x future is equal to, follows the same dynamics as this. Okay, so basically the first J future would be just the objective function evaluated at the current point, and then the after a few iterations, the J future is going to be future J's, right? And also all of these future objective functions are multiplied by the same quantities over here, right? So before we evaluate this future objective function, let's actually compute this part. Okay, so the second part after we have G is actually very easy to compute. The second part is equal to just the perturbation itself. Actually, I want to actually compute the second part before we change the before we make this change. So that is 1 second. Right, that is because I need the pre-image of y, right? So basically the pre-image of y is just the x before we perform these iterations, and that is equal to, let me just do this. That's the perturbation itself, and times the G, but the G is evaluated after the iteration. G is evaluated at y, right? So we want to do this after G has been updated, but before x has been updated. So that's the second part. Okay, the first part would also need the first part is let's see, is the derivative of the perturbation itself with respect to y, and the perturbation, so okay, so it is right, the derivative of the perturbation with respect to y, which we have to make a change of variable. So this is the derivative of the perturbation with respect to x times dx dy, right? So this is the so this is basically that makes it numerically easy to evaluate. Okay, and this is let me see, second part, the first part is equal to the derivative of the perturbation. The perturbation is sine of this, so derivative is 4 times cosine of 4 times x0. So that's the derivative, and then we want to multiply it with a 1 over slope dot real. Okay, so that's the dx over dy, so that's 1 over the slope, right? And that's it. That's the first part. Okay, and the density is going to be multiplied with the outer density to form the equilibrium density. Okay, and then every time we compute the J future, let's see. So basically, dj is going to be equal to plus equal to j, actually minus equal to, there is a negative sign, j future, multiplied with the first part plus second part, right? And we'll take the minimum over this. So say dj, let's also make it an array, and this is dji. Let's make it dji is equal to 0 for now, and afterwards we'll dj dot append dji. So this is going to be the entire loop. Matched parentheses. Yeah, 2 times. Yeah, so this is the entire loop where we computed the j over every iteration. We also computed the contribution to dj over the entire iteration. So if we plot j, we should be able to see the time history of the averaged objective function, and also the time history of the averaged sensitivity computed. So this is the objective function, and this is the sensitivity. Okay, and we can roughly estimate how good the sensitivity is by remembering that at s is equal to 0, the objective function is going to be exactly equal to 0, right? The objective function is a cosine of 2x, which averaged over a uniform density is equal to 0. And now we have perturbed s to 0.1, right? And the objective function dropped from 0 to roughly about I don't know, let's see, let's print j dot mean j, print mean dj. So the objective function should have dropped from 0 to about minus 0.0, maybe minus 0.07 or 8. So let's see what the number turns out to be. Okay, 0.08. And the dj represents the derivative of the objective function, right, with respect to the parameter. It turns out to be about minus 0.65. And I remember we previously did plot the trend of the objective function over a small range in the parameter, right? So this is roughly the trend in the parameter. So basically we have been computing the slope over here, which is slightly less than the averaged slope from 0 to 0.1, right? So what we computed to be minus 0.6 seems to be pretty correct. Okay, so that is our general. Basically, this lecture we have covered with a pretty fast speed, a general way of computing the sensitivity of a long-time average objective function when we are perturbing the dynamics. And the dynamics is the general dynamics that have stable and unstable directions. But we have been restricted to the perturbation exactly along the unstable direction, right? Okay, and so this is really the most difficult part of doing sensitivity analysis for chaotic systems. And in the next week, we are going to further generalize to a perturbation. First, to a perturbation that's going to be have components both on the stable and unstable directions, and then to continuous dynamical systems where we have perturbation in the stable, unstable, and the neutrally stable directions. Okay, so this is always going to be a component in that analysis, and we'll show how do we split the perturbation into different directions, just like we did in time dilation, right? Unstable, stable, and neutrally stable directions. And we'll be using this algorithm for the unstable perturbation, and we'll be using similar algorithms as we did for the periodic limit cycles for the stable and neutrally stable cases. Okay, so see you next week. And for those taking the class, I'll be contacting you to schedule meetings with me for like how do you plan to do your final project. All right, and we'll focus on something that's a chaotic dynamical system, and ideally should have all the stable, unstable, and neutrally stable directions. And we'll see what you want to do with these systems. Okay, I'll see you next week, if not earlier.